Hi guys, it's me, Sir Ernest, and today we're going to talk about the loaded string. So when we say a loaded string, it is a string of particles of mass m that is separated by distance d. So for example, we have two fixed ends for that string. So in other words, your string will be fixed in two ends, and then let's say this particle is the particle closest to this end, and this particle is closest to this end. Then this is adjacent to another particle, this is adjacent to another particle, and in between these two particles we have several particles. So let's say that particle is represented by this particle. Let's call this particle n. Okay, and this is adjacent to this particle before that and after that. Okay, so that means this is connected, these are connected, and these are connected, and in between this one we have several particles. So as I mentioned earlier, each particle has mass m, and let's say we have n particles. So what do we mean by that? Okay, so if this is the first particle, this should be the second particle. If this is the small n particle, so this particle is a representative of all the particles in the string. So that means this would be n minus 1 particle, and this is n plus 1 particle. So if you have n, capital N number of particles, this will be capital N, and this will be capital N minus 1. Okay, now the distance between the particles are d. So that means if this is our origin, the distance from this origin to the first point would be d. So therefore this is 2d away from this point, etc., etc. Okay, so this is nd, this is n plus 1d, and this is n minus 1d. This is capital N minus 1d, this is capital ND. So therefore the end of your string would be n plus 1d. As I mentioned earlier, this is fixed, this is fixed. Okay, now before we proceed, let's have some assumptions first. So number one, the tension on the string so number one, the tension on the string is constant. Okay, number two, the masses move in the vertical direction. So what does it mean? It means that we're only going to look into the y direction. Okay, so if this direction is your y, we're not going to deal with any vibrations or any motion of each of the particle along the x direction. Okay, so that means only the if your tension, let's say, is given by tau, only t tau along y will be considered, because the x component of your tension does not involve any motion along that direction. Okay, number three, the string is elastic. So that means the potential energy associated with this motion will be from the string, and that is an elastic potential energy. Okay, and because of that, we're going to neglect gravity. So that means the potential energy associated with the string will be the total potential energy. Okay, so that means the only force acting on the particle will be the tension. And we already said that it is elastic, so therefore it has an associated potential energy. Now, to solve this problem, so that is the position function, okay, along the vertical direction of each individual particle must be, well, will be obtained by first looking for the force acting on, let's say, one particle. Let's say that particle n, because we already said that n is a representative particle. So let's look at that particle. Okay, so for example, this is the equilibrium position. Okay, and let's say this particle is here. So this is, say, particle n minus 1, and say this is where n particle is, and this is the adjacent particle n plus 1 particle. And let's say this particle moved in the vertical direction by this amount, this particle by this amount, and let's say this particle by this amount. Okay, so let's call this yn. Let's call this yn plus 1, and let's call this yn minus 1. Okay, so as I mentioned earlier, this is where your particles are. Whose masses will be n. Okay, now because this is your representative particle, so we assume that with n plus 1 there is another particle connected somewhere there, and with n minus 1 there's another particle connected somewhere there, and this particle is connected to this particle. Okay, let's say okay, let's represent that by green. Okay, and this one will be okay. Now again, as I mentioned earlier, this will be your equilibrium position. Okay, so the distance between this and this and this and this will be d. Okay, now we are set up. Now let's look at this assumption. So when you say the tension is constant, so that means the particle n, which is connected to the two other particles n minus 1 and n plus 1, so this means this string and this string have equal tension. Okay, so let's say this is your tension, and this the magnitude will be equal to this tension. Okay, but as mentioned here, the vertical direction is the only direction that the particles move, so that means only the vertical direction or the vertical components of the masses will be considered. So in this case, this tension and this tension will be considered, and this is related to this angle and this angle. So let's call this theta n minus 1, and let's call this theta n plus 1. Okay, so from here, the net force, Okay, from here, the net force will now be equal to tension by n minus 1 and the tension by n plus 1. Which is equal to negative tau, which is the magnitude of this will be the same as this. Then sine, okay, good. This is sine theta n minus 1. And this is minus theta at tau times sine theta n plus 1. Okay. So if we're going to look at this, we can see that sine sine theta n minus 1 will be equal to yn minus yn minus 1, right? So this is yn minus yn plus 1, so this is the length divided by this length, which is the square root of d squared minus or plus yn minus yn minus 1 squared. But since our vertical direction, sorry, I forgot to mention earlier that the displacements are small, so that means, okay, so if the displacements are small, so that means this distance is much less than this distance. Okay, so in other words, yn minus yn minus 1 is much less than d. So that means if this is much smaller than d, and then you square it, so therefore this term becomes negligible. So this will be approximately equal to yn minus yn minus 1 over d. Okay, same goes for sine theta n plus 1. Okay, so that means we're now going to rewrite the net force to be negative tau times yn minus yn minus 1 divided by d minus tau times yn minus yn plus 1 over d. And this is equal to my double dot for this particle n. Okay, as you notice that if you're going to summarize this or simplify this, we now have m yn double dot equals tau over d, so factoring out tau over d, and then this becomes negative of yn plus 1 and negative of yn minus 1, and then minus yn minus yn. So the end result would be yn minus 1 minus 2 yn plus yn plus 1. So this is now our equation of motion. And as you will notice that this is a coupled differential equation. Okay, because that means the acceleration of particle small n also depends on the displacement of its adjacent particles. Okay, so now we have set up our equation of motion. So in the next video we're going to solve this differential equation. Okay, so for now that's it. I hope you learned something today, and I'll see you guys in the next video. Bye bye.